Okay, thanks for having me. I'm going to talk about the dust growth in rings by the dusty Rossby wave instability. As we know, for the dust growth, we have micron-sized dust particles in the disk that will eventually grow into thousands of kilometer-sized planets. So this process will roughly divide into 3 stages. In the very early stage, we have micron-sized dust particles grow into centimeter or millimeter-sized pebbles. The micron-sized particles, they can collide and stick together. And in the intermediate stage, we have pebbles that will go into the kilometer-sized planetesimals. In this process or in this stage, the sticking is stopped because of the bouncing or fragmentation barrier in the inner disk and due to the fast radio drift in the outer disk. And we think the streaming instability is possibly the leading mechanism that could lead to the pebble growth into planetesimals. So in the late stage, once we have planetesimals formed, the planetesimals can create similar sized planetesimals, or they can also create like smaller pebbles to reach to thousands of kilometer-sized planets. So in this talk, I'm going to focus on the intermediate stage for pebbles that grow into planetesimals. And as I just discussed, the streaming instability is possibly the leading mechanism in the stage. But on the other hand, we know that rings and gaps are still commonly observed by ALMA, and these rings, they are the dust continuum emission. So that means we have dust particles concentrated into the substructures. Okay, then we ask the question, do particles still clump to form planetesimals in ALMA rings? And to answer this question, we probably need to know a bit about the gas structure for a ring. So for the dust particles to concentrated in a ALMA ring, we probably need a pressure bump. So on the right-hand side of the pressure bump, or like the center of the pressure bump, we have stop capillary motion for the gas, and the dust, because it's pressureless, is always in capillary motion. So the dust will drag by the gas into the center of the pressure bump. And on the left-hand side, we will have the supercapillary motion for the gas, and the dust is always in capillary motion, so the dust particle will be dragged into the center of the pressure bump. Okay, then in that case, on both sides, we have dust particles drift towards the center of the pressure bump, and direction of the particle acceleration is towards the center. So that's how we can form a ring-like substructure. Okay, and back to our question, do particles clump to form planetesimals in rings? There could be 2 perspectives we can explore. The first one is can we still have streaming stability work in rings? So the linear analysis of the streaming stability, most of the time, like in the literature, is conducted in the local Schrödinger box model, which means the pressure gradient is always a constant. And the streaming stability requires this pressure gradient to be non-zero because we need the relative drift between the gas and dust. But in the pressure bump, especially in the center of the pressure bump, the pressure gradient vanishes exactly at the ring center. So that could be one of the problems for streaming stability to operate in the ring. The other problem is about turbulent diffusion. So once we have turbulent diffusion, the numerical simulations show that it depends, the planetesimal formation by streaming stability in turbulent diffusion gases depends on how you incorporate this turbulence. If you use forced turbulence in the simulation, which means you periodically inject the velocity perturbations in the simulation, that will lead to this pressure or the weakened of the streaming instability, also the planetesimal formation. But if you conduct MEG simulations, which will self-consistently induce a pressure bump, then that will actually enhance the planetesimal formation due to this pressure bump, which I will discuss later in this talk. So that is the first perspective for the streaming instability. But for this talk, I'm going to focus on another mechanism that could be set in the ring to help the formation of planetesimals, and that is the density-Rossby wave instability. So to understand the density-Rossby wave instability, let's look at the pure gas Rossby wave instability at the very beginning. So if we have a pure gas like the fluid, and we have a pressure gradient for the gas density in the radial direction, the nonlinear evolution will give us several large-scale vortices in the azimuth direction. Okay, there we go. And that could be the underlying mechanism that drive the azimuthal clumps or azimuthal asymmetries for the observations. And if you look at the density-Rossby wave instability, we need to add some more equations like the dynamical equations for the dust. What we have here is the continuity equation for dust, obviously, and also the momentum equation of the dust. And there are several terms we need to incorporate. The first one, of course, is the drag force on both dust and gas. And the second one is the turbulent diffusion. For the gas is viscosity, and for the dust is the dust diffusion term. And finally, we need a forcing term in the system, because this forcing term can mimic the physical mechanism that can create a pressure bump in a system. So this forcing term is in the azimuthal direction, it's in the y direction, which means you will have a positive torque on the left-hand side of the pressure bump and a negative torque on the right side of the center of the pressure bump. That will give you a density, like a Gaussian profile density or pressure bump. Okay, once we have these dynamical equations, we need to establish this equilibrium state or the steady state. And this, for this analysis, this is a linear analysis, and we assume the steady state will have that gas density or pressure, a Gaussian profile. And for the dust density is obtained or calculated from the dynamical equations is nearly a Gaussian profile. And the width of the dust density Gaussian profile is determined by the balance between the radial drift towards the bump center and the turbulent diffusion. So in this plot, the solid red curve is for the gas Gaussian profile, and for the dust, the green curves from left to right, we have alpha viscosity from small value 10 to minus 3 to large value like 0.1. So that makes sense because once you have like very small diffusion, like very big diffusion, the width of the dust density profile is very narrow. And if you have strong diffusion, then the dust density profile could be like much wider. And then we have the dynamical equations and the equilibrium state. We can do the linear analysis to find the growth rate of the density-Rossby wave instability. And this is the system of eigenvalue problem, which can be solved by the spectral method. And what I use is the Daedalus project to solve the eigenvalue problem. The spectral method will give you the growth rate of the density-Rossby wave instability. And in this plot, I'm showing the growth rate of the instability as a function of Ky, which is the azimuthal wave number. The parameters going here, we have gas bump width, which is fixed to 1h. And the viscosity is relatively small, it's alpha equals 10 to the minus 3. And for different panels, I have different dust bump width and different dust to gas mass ratio. So from top panels to the bottom panels, I have wider and wider dust bump. It starts from 0.05 H and eventually it goes to 0.3 H. And from right to left panels, the dust to gas mass ratio goes from 0.1 to 0.5. And look at this plot, we actually got two types of dust speed Rossby wave instability modes. We call it type 1 modes and type 2 modes. The type 1 modes are displayed in crosses and type 2 modes are in plus symbols. So type 1 modes, we find it is that's modified pure gas RWI, and for the type 2 modes, they arise due to the coupling between the dust and gas. And the type 1 modes, they can set in for a very big range of parameter space. In this plot, you can see all of the panels, they have crosses, which are type 1 modes. But for type 2 modes to set in, it's only set in for very high dust to gas ratios and also for narrow dust bumps. Okay, then we also look at the vorticity or vorticity profile for the RWI modes, because the vorticity is actually the source of this instability. And for the type 1 modes, we found they are driven by the advection of the background vorticity or vorticity into the perturbed vorticity, as shown on the left-hand side. And for type 2 modes, they consist of two waves. We see the classic Rossby waves across the pressure bump, and we also see the very thin waves, which are driven by the drag force between the gas and dust. And these thin waves are specific for the type 2 RWI modes. Okay, then in the literature, people conducted numerical simulations. They are showing box simulations for the RWI, and starts from different initial conditions like different bump width and bump amplitude. They do find two types of the RWI modes in the nonlinear stage. For the type 1 modes, they find in the nonlinear stage, the ring-like structure eventually is disrupted and a large vortex is formed in the simulation. And for the type 2 modes, we find the rings can retain the simulation like for long opto times, about 500 opto times, and there are dust clumping in the simulations, as you can see here. So those are the evidence of planetesimals formation. So type 2 modes are considered for the possible underlying mechanism for the planetesimal formation in ALMA rings. And then we apply the parameters of the dust bump from D-sharp sources, the D-sharp rings, to the linear analysis of the RWI. And the bump parameters we find is for the dust, we just fit the Gaussian profile, and we find the amplitude for the dust density and also the width for the dust Gaussian profile. And for the gas bump width, we use the rotational profile to constrain the width of the gas bump. Because if you're in the pressure bump, the rotational profile is going to be either super-Keplerian or sub-Keplerian. But if you go far away from the bump, it's going to be more like a Keplerian motion. And for the amplitude, the ratio of amplitude of dust to the gas, we just use 0.1 because that's roughly equal to the dust to gas density ratio, and we assume it's 0.1 in the ring. Okay, so what we find once we apply those parameters in the linear analysis of the RWI, we find the type 1 modes, they can emerge in 1 out of 4 rings. And this is actually consistent with ALMA observations, because we say only about 10% of disks, they can have azimuthal dust clumps in the observations. And for the type 2 modes, we find type 2 modes are completely absent in all 8 armor rings. And that could be due to there is no type 2 modes emerging in this in the real disks. Or the other possibility is that due to the limitation of spatial resolution, the intrinsic dust ring could be narrow. And that, if the intrinsic dust ring is narrow, then type 2 modes can still have the chance to emerge. Okay, so that's about the that's the Rossby wave instability I want to talk about. In the second part of this talk, I'm going to jump to the MG simulations, which can induce the pressure bumps and concentrate dust particles in array. So to understand the MG simulations in disks, we need to have some background introduction on the ionization fractions. The ionization fraction can have thermal ionization or non-thermal ionization. The thermal ionization depends on the temperature in the disk, which is primarily passively set by the irradiation from the central star. So if we go to the very inner region of the disk, say less than 0.1 AU, the temperature is very high, it's reaching 1000 Kelvin. The gas is fully ionized in this region, which means the gas and magnetic fields, they are coupled very well, and we are in an ideal MHD regime. But if we go to the outer region of the disk, larger than 0.1 AU, then the temperature is lower there. So the thermal ionization is very weak, and the non-thermal ionization in the outer disk by stellar X-ray, far UV, UV radiations, and also cosmic rays, they are also weak. So in the outer region of this larger than 0.1 AU, the disk is extremely weakly ionized. Gas is not perfectly coupled with magnetic fields, and we need some non-ideal MHD effects to describe the gas dynamics. And there are, in general, 3 non-ideal MHD effects in total. We have ohmic resistivity, the Hall effect, and polar diffusion. So the ohmic resistivity prefers high density regions, so it dominates at the midpoint of the disk and the inner region of the disk. The ampolar diffusion prefers low density, so it's in the outer region of the disk and the surface of the disk, and the Hall effect is in between them. Okay, so I'm going to show 2 MHD or non-ideal MHD simulations for disks. One is for the inner disk, and the other one is for the outer disk. For both simulations, it's 3D simulation, and they use the static mesh refinement, so we have finer grids at the midplane, and the grids becomes closer towards the poles. And this is a movie showing how the MHD maximum can induce pressure bumps or like the magnetic flux concentration phenomenon. So on the left-hand side, I have the radial velocity of the gas. In the middle is the vertical magnetic field, and on the right-hand side is the azimuthal magnetic field. I'm just going to play it another time. So if we look at the left panel, you see some turbulence going on in the gas, and that is non-ideal MHD weakened MI turbulence. And if you look at the middle panel, you find that the vertical magnetic fields, they are actually concentrated at multiple radial locations in the disk. And this concentration of vertical magnetic fields, they are crucial for the pressure bumps to form. Okay, so the physical picture of the magnetic flux concentration is that initially we have a smooth distribution of magnetic fields, but eventually in the simulation, you will find the vertical magnetic fields, they are concentrated at the different radial locations in the disk. Those places where the magnetic fields are concentrated, they will launch very strong magnetized disk wings, which means the gas is depleted in those regions. So what you see in the gas radial profile is that the surface density of the gas shows minimum at the location where the magnetic fields are concentrated. And this magnetic flux concentration leads to the rings and gap structures in the gas. And these two plots are showing for the inner disk simulations. In the outer disk, we also see the same or very similar phenomenon. We see the magnetic flux, the vertical magnetic flux are concentrated, and also we see the radial variation of gas surface density. So once we incorporate the dust particles into this MHD simulations, we do find the millimeter or centimeter dust size, the dust particles, they can trap into this pressure bumps induced by the MHD, or induced by the the flux concentration phenomena. And once we do the synthesized image, we do find this rings and gap structure showing due to the MHD mechanism. Okay, this is my summary slide. So in the first part of the talk, I discussed the dusty Rossby wave instability. We incorporate the dust dynamics and also the dust back reaction to the pure gas RWI, and we found two types of the RWI modes. For the type 1 modes, we find is dust modified pure gas RWI. For the type 2 modes, they arise from the coupling between the gas and the dust. And when we're applying the ALMA ring parameters to the type 1 and type 2 modes, we find type 1 modes can set in for 1 out of 4 rings, but for the type 2 modes, they are completely absent. For the MHD simulations, those 9D MHD simulations for inner and outer protoplanetary disks show magnetic flux concentration phenomena, and this phenomena can lead to the gas pressure bumps, which can trap dust particles and form rings. Okay, I'm going to stop here and take questions.
So, hi, Alex Yampras, LMU Munich. Thanks for a great talk. I want to ask about your MHD rings that you see there. Do they reach a steady state where the rings have now a fixed spacing between them? And if so, can we predict the spacing between rings?
So the spacing between the rings, they are actually more stochastic once you change like the, so for the outer disk, we have ample diffusion as 9D MHD effects. If you change the AM, like the SS number for ample diffusion, you'll find the spacing could vary a little. It's on the range of like H.
And do they remain stable, or will they at some point start merging together?
Yeah, so some of them are quite stable, like in this plot, right? You can see, so the y-axis is the evolutionary time in the simulation. So for the left one, it's like quite stable because it stayed at around R equals 5 or 6. But for the right one, you see those flux concentration can emerge, or some of them can actually split. So it really depends, probably on the AM.
Thanks.
Okay,
Hi, very nice talk. This is Ji Wang from the Ohio State University. I have a clarification question for the first part of the talk. So you're saying, am I understanding correctly that the type 2 mode would be the mode to create planetesimal? And if so, if you find none of the 8 or 9 disks here produce type 2 mode, does that mean that covering ALMA disks are no longer able to create planetesimals?
Right, there are a couple of possibilities, right? So if the so the reason behind this is that the width of the dust bump is too wide for the type 2 modes to operate. That's what we find from our linear analysis. But the intrinsic dust ring width could be narrow due to the limitation of the spatial resolution of ALMA, right? So if the intrinsic dust bump width is narrow, there are still the possibility for the type 2 modes to set in. And another possibility is that the rings width, they are already the outcome of the type 2 modes.
Thank you.
Hi again. Is it appropriate to say that the type 2 modes try to stabilize against the formation of vortices, but the type 1 modes try to power a vortex?
Yeah, so from this local sharing box simulations, that's the case, right? If you look at the type 1, the anomaly stage of type 1, they show a big vortex in it. The ring structure is disrupted. But for the type 2, you see the ring can retain for a very long time, and you see that's clumping in these rings.
So then is it reasonable to say that something along the lines of, we don't see the type 2 modes because they anyway try to prevent vortices from happening, so it's self-fulfilling?
Not really, because vortex is only 10% of the disk observations show they have vortex, right?
Right.
Yeah, so you don't need every disk to have a vortex. So don't expect type 1 modes to emerge in all of the ARMA rings. Otherwise, you will have each ARMA disk to have a vortex.
Yeah, my point would be that if you saw a type 2 mode, that would mean that you see a vortex being disrupted, which anyway you don't see because there's no vortex. Does that reasoning make sense, or is it wrong?
I think it makes sense, yeah.
Right. Thanks.
Bennett Skinner, McMaster University. Your findings of whether or not you had Rossby wave instability, how resilient are those findings to varying the alpha and the Stokes parameter that you assumed?
Yeah, so for this plot, the alpha is 10 to the minus 3. That's quite representative for protoplanetary disks. In some disks you have lower alpha, some disks you have higher alpha. We find that if your alpha close to 0.01 or 0.1, both of the modes, the growth rate can drop because the diffusion is too strong. But if you lower the alpha to 10 to the minus 4, then the type 1, type 2 modes, they are very similar to what I showed in this plot.
Okay. Just to briefly follow up, I get that overall, but for specifically the 4 systems that you looked at, I think I saw at the top that you'd assumed.
I assumed the alpha is 10 to the minus 3. I didn't use. Yeah.
If you vary those parameters, do those results change at all?
It won't give you a huge range for the results as I tested.
Okay, thank you.
Yes, it's a short question. So you mentioned that the occurrence of your type 1 modes agree with the number of these that we see asymmetries. And if we look beyond the chart, we see that asymmetries are more common around herpes stars. So I just wonder if from the models, if the type 1 modes are dependent on any of the stellar or these parameters.
I would say it more depends on the width and amplitude of your ring rather than the stellar properties. If the stellar properties can adjust to the properties of the rings, that may be the case.
Thanks.
Ralph Budritz, McMaster. In your lovely simulations here, it seems to me that the concentration of magnetic flux is a property of many different kinds of MHD simulations now. You and other authors have shown this. So it's probably a general phenomenon, and I wondered if you had some understanding of that mechanism.
Yeah, so that's a good question. For the magnetic flux concentration, we find that both in local simulations, global simulations, for ideal MHD simulations, non-ideal MHD simulations, but the underlying mechanism is still under debate. One possibility is that, well, I guess there's no consensus yet to understand the underlying mechanism, but it's very robust for the MHD simulations.
Any other question?
Hey, Eric Ives, University of Hawaii. So I wanted to go back to Alex's question, which was whether or not there was some sort of regular spacing. And if I understood you correct, you said it was more stochastic. But would you mind putting up the very nice plot where you actually had the dust added?
There's no dust in the simulation.
No, sorry. There was another one where I thought you there, that one.
Yeah.
Yeah, that was Who 24, right?
Yeah.
That was a paper with John Lon, right? Jahan's paper?
Okay. I mean, it looks pretty regular. Looks like there's a characteristic space to me.
Right. So for this one, I think for this one, this is possibly a 2D simulation. And I don't want to say this, but it's possibly due to the resolution of the simulation.
That it may be an artifact.
So the physical mechanism to derive this flux concentration could be a little different from my simulation, which is 3D and which has higher resolution to resolve the MRI.
And if, may I ask a follow-up?
Yeah, you might. Yeah, go ahead. We're doing follow-ups this period.
We're doing ping pong. So the other question would be whether or not this generation mechanism is robust to what is happening at the sort of dead zone MRI interface, because we see, of course, disks with lots of structure and disks with very little structure. So is there some sense where we could get some predictability of when this would occur?
Right. So the simulation is not the MHD simulation. If you go to the interface of MI, dead zone edge, then it's a good question because the simulation, most of the simulation doesn't has the transition from the dead zone to non-dead zone. So most of them are like purely IDMHD or purely non-IDMHD.
Okay, last short question.
Yes, no. Are these rings Rossby stable?
These rings, in my 3D simulation, they are Rossby stable.
They are not.
They are stable.
Oh, they are. Okay.
They are.
Okay, let's thank our speaker again. Very good.